Okay, welcome everybody. Welcome to the safety webinar on the data fusion for non-motorized safety analysts. My name is Eric Glenn, and we're going to start right on time. And as people flow in, we will be admitting more people. First off, I just want to thank the presenters and thank all of you for joining our webinar. This is the last webinar of the year. Exciting. It's been a fast year. So, want to first, like I said, introduce myself. My name is Eric Glenn, and I am the program manager for safety. We appreciate you joining the webinar on data fusion for non-motorized safety analysts. And you have all come into the meeting muted, and we would appreciate if you stayed muted until the Q&A session has begun. If you have any questions during the webinar, please type them in the chat box and they will be addressed at the end. The chat box is usually right underneath. You should be able to just move your cursor towards the bottom middle of the screen. You'll see chat, and you can just click that and type whatever you need to in the chat box. I will also like to say we will have captions on for your convenience as well. And at this time, I would like to introduce the presenters. First is Dr. Epoch Sensor. She's a research scientist at the Texas A&M Transportation Institute. Her research focus lies at the intersection of social, behavioral, and science in bringing together the elements of mobility, safety, equity, health, and technology. She is in graduate committee faculty of Texas A&M University and is a faculty affiliate of Texas A&M Center for Population Health and Aging. She serves on the board of directors of the International Professional Association for Transport and Health, as well as Phoenix Mobility Rising, a nonprofit organization focusing on mobility as a service for vulnerable and underserved populations. Dr. Sensor is an active transportation research board committees and serves in the editorial board on TRB's journals. I would also like to introduce Sylvie Manura. Sylvie attained her PhD degree from Texas A&M Transportation Engineering. Her main area of research is non-motorized planning, distracted driving, with a goal was to facilitate pragmatic, scalable, and statistical rigorous solutions to promote safety for teen drivers and non-motorized traffic. And at this time, I would like to turn it over to Sylvie.
Indeed, I think it will be me. Yes.
Oh, my apologies.
No worries at all. Yes. I just want to make sure that everyone is seeing the slides right now. Sylvie, do you see the slides?
Yes, I can see the slides.
Perfect. Okay, that's great. Thank you very much, Eric. Thank you very much for the great introduction. My name is Epoch Sensor, and it's a pleasure to be here. Thank you very much, everyone. And it's a pleasure to present at this last safety webinar of 2021. I hope 2022 will bring much better days to all of us. So during our presentation, Sylvia and I will try to provide you a high-level view of our project. I will start with an overview and discuss key components needed for the fusion. Then Sylvie will have a bit more deep dive into the characteristics of fusion, followed by its implementation into non-motorized safety analysis for our study area. So as we all know, there have been many efforts to promote biking and walking in the nation to create healthy, sustainable, and equitable communities. Unfortunately, though, non-motorized activities still contributes to a disproportionate share of total fatal and serious injury crashes. So acknowledging this issue over the years, there has been an increasing demand for evidence-based, data-driven strategies to reduce non-motorized crashes which has eventually resulted in a growing body of literature in the field of safety. But in most of these efforts, non-motorized demand or exposure data was the missing piece of the puzzle, mainly preventing us to accurately assess the risk and address the safety concerns. And this has been primarily because of the lack of data or limitation in accessing the data or lack of resources in processing this data. But today, thanks to advancements in technology and data analytics, we are now in a different stage and have access to more data sources that could be complementary to each other and could add a lot of value to non-motorized safety analysis. We can categorize the current non-motorized data sources into three main categories. The first are more direct ways of collecting the data, either through traditional sources like traffic counts or surveys, or emerging sources or the crowdsourced data, such as the location-based service data or tracking app data, which can come from bicycle tracking app, fitness tracking app, or some other app. And in addition to this, we can also get this data a bit more indirectly after processing through various different modeling-based methodologies, such as direct or facility demand models, regional travel demand models, or models that would rely heavily on GIS tools or GIS-based measurements in determining activity levels. So given various sources, non-motorized traffic activity data exhibit unique characteristics. The data vary in temporal and spatial and population representation. There are differences in data formats or forms or sample size or how biased or not biased the data is. So each of these sources, as we know, come with their own strengths and limitations. Therefore, a single model or data source is often unable to provide enough coverage and reliability to help with non-motorized safety analysis as an exposure measure. The fact that no individual data source or model is sufficiently adequate drives really our research question of this project, indicating whether combining or integrating multiple data sources, or in simple terms, creating a data fusion can produce or can help produce a better estimate of non-motorized demand or exposure. So in this respect, our primary objective in this project was to develop a fusion-based technique or methodology or framework to combine multiple non-motorized data or exposure data and evaluate its effectiveness as well as its potential use cases. The concept of fusion is well established, and there have been various different applications really, but due to these numerous emerging applications of fusion approach in both research and industry practice, it's yet to reach an equilibrium in terms of terminologies or the tools to use. Really, we don't really yet we don't really have the consistency in the definition or terminologies. But in its very simple definition, data fusion can be defined as an approach to combine or integrate multiple data sources to present comprehensive information. And researchers across various different fields, various different disciplines have acknowledged its advantages to obtain rich information, especially when there are multiple sources of similar data with distinct characteristics. But there's not really one fits to all approach or framework or a fusion mechanism. And this is especially the case when it comes to non-motorized data and diffusion, which can be considered as an emerging field. So as I mentioned earlier, non-motorized data, traffic data sources are quite varying in terms of resolution, whether it is spatial, temporal, or population, and are most often generated in different data formats. This then requires the data to be processed to reach a homogenized representation before we can apply any fusion. And the processing steps and complexity depend on the format of the raw data and the scope of analysis. So when we think about this, together with most of the times the limited sample size for non-motorized travel data, is really emphasizing the need to develop appropriate fusion methods that would be reflective of the unique characteristics, unique data characteristics. Therefore, Sylvia and I and our other team members really did spend quite a bit of time to explore, select, and customize fusion mechanisms. We then adopted a specific fusion mechanism named decision fusion that can accommodate the distinctive nature of the non-motorized traffic activity data or the model output. Sylvia will go in more details about this in the next slides, but just to give you an idea, the decision fusion can be considered a type of data fusion, and it's a mechanism to combine information where we pull a decision from each source to obtain a unified decision. And it's particularly useful to obtain a more accurate decision when there are uncertainties and constraints associated with the data, which is most of the times the case, at least for our project, was the case for non-motorized data. So keeping all this in mind, for the development and application of fusion for our case study, we have developed a three-stage research framework. This included processing or homogenizing the non-motorized data sources at a given scope for the study area, exploring, utilizing, or developing and applying the fusion mechanisms, and utilizing these fuse estimates for crash analysis. So in terms of our study area, we selected City of Austin, which has a strong commitment to its Vision Zero goals and long-term planning to improve non-motorized infrastructure and increase safety and mobility for pedestrians and bicyclists. We focused our attention to bicyclists. We selected the annual average daily bike AADB volume at intersections as our scope of estimation. But although we selected all these for the utilization of the fusion framework, the data analysis, the fusion framework, or the models that we have worked on as part of this project can be adapted for both pedestrian and bicycle traffic. They need to be adjusted, they need to be revised because they are heavily based on the regional characteristics, local characteristics, or data characteristics, but they are quite scalable and can be applied for different modes and other geographic scales. So for the study area, we gathered data from 5 primary sources relevant to bike activity. These included the actual bicycle volume counts, whether they come from the short counts or the permanent counts, the bike sharing data, the National Household Travel Survey data, the TechStat add-on version that we had for 2017, and Strava and Streetlight data. So I should emphasize at a moment that this project was quite data hungry because of its goal. But we really did get great support from various partners in compiling, in accessing different data sources to be used in the project. So we were really lucky that that provided amazing help for the conduct of the project. So in addition to these primary data sources, we also compiled secondary data sources. Some of them came from publicly available sources and from different platforms, such as the data related to socio-demographic characteristics, or land use characteristics, or the bike network data, for instance, we needed for building the models. And each of these raw data sources went through exhaustive processing to compute AADB, excuse me, at the intersections in the study area. We did have a bit more than 2,500 intersections for both, covering both signalized and unsignalized intersections. So we then use these data to develop 5 different demand models, bike demand models. This included a direct demand model, which is the most frequently used modeling approach in bicycle and pedestrian safety, where we use the actual count data and various different explanatory variables to estimate demand at the intersections. And then we use the Campo travel demand model components and its data, as well as the most recent NHTS data to develop a 4-step model. We benefited from the already existing model and then processed some of the data and then extracted the bike trips from there. In addition, we did develop a bike sharing model using the Berkshire OD tables that we had obtained for all available stations in the city. And finally, we developed two crowdsourced models, one using Strava data and the other one using streetlight data to estimate bike counts at intersections where the data was available. So this mainly included the processing the data, bringing it together, and then applying a population scaling through different modeling efforts so that we have the same homogeneous level of data. And at the end of all this process, each of these models produced ADB estimates, the bike volume estimates that we were interested in for this case study area at the intersections covered by the corresponding model. And then in the next step, we use these estimates as input into the fusion algorithm. And now Sylvie will go through the details of these fusion algorithms that we considered and what we have done in particular in developing and applying the fusion mechanism.
Thank you, Ipek. Hi, everyone. I'm Sylvie Shirajum Munira, and I'll be going more into details about the fusion mechanisms and the algorithm we used for our project. So when we started diving deep into the concept of fusion, I realized there are several characterizations in the literature, and fusion are often characterized in multiple steps or levels, or sometimes they're used in there are different aspects like hierarchy or the architectures. And what I found really interesting was that the fusion concept has been represented using multiple terminologies in the published literature, but there is not really a standardized categorization or consensus, and the terminologies are most often customized to the field of application. So some literature suggested to use data or information fusion as an overall term for fusion, whereas the sensor or multi-sensor fusion of like a raw sensory data is a subset of information fusion. We can say that. Can we go to the next slide? Thank you. Decision fusion refers to actually the high level of fusion, which takes the symbolic representation of events to obtain a more accurate decision, which is the main framework for our study, as we mentioned. This concept has already been applied in different areas, including in transportation, such as for analyzing crash, speed, traffic volume, etc. And the world of decision fusion is also vast. It has many aspects for consideration and different potential algorithms that vary across the aspects. For example, outputs can be crisp or abstract level, as in our case. It can also be rank or measurement level. It means that each estimate comes with a probability. And we can have trainable and non-trainable models, like trainable models such as Bayesian. The fusion framework also depends on the availability and the size of the benchmark data. For example, voting method really doesn't need any benchmark data, where the behavioral knowledge space needs a large data set for training. And there are also frameworks that can consider the conflict and correlation of the pieces of evidence, which are often required in certain cases. So I think it's a good place to sum up a side-by-side comparison of the non-motorized data characteristics and decision fusion. So the data is generally, for our cases, the data for non-motorized traffic, the data is generally available at abstract level or crisp level. And the data is most often challenged with uncertainties and constraints such as low or unavailability of the ground truth data or actual observation. And the most importantly, data for one location, we cannot say that even they're located nearby, the one location data is not representative of the another location. They can be vastly different. So this is one of the characteristics we had to consider. And while I already mentioned the basic definition of decision fusion, I will go into more details exactly why we have chosen this method for our analysis. So as I mentioned just a while ago, there are several decision fusion algorithms. So as our data were abstract level or crisp, I will briefly mention the most frequently used algorithms for dealing with the crisp level data. So there are voting-based rules, which involves consensus pattern among the sources to make a final decision. There are behavioral knowledge space that needs a large amount of data to record the behavior of all the classifiers on a set of samples. There can be Bayesian inference. And then there is Dempster-Shafer evidential reasoning, which has a special way to handle uncertainties and ignorance of the data. So considering the characteristics of the output of the non-motorized activity information, availability of the ground truth data, sample size, this research actually adopted multiple fusion mechanisms, which we divided into two categories, fusion with and without benchmark data. In the first category, I will explore the commonly used voting approaches of different rationale. And then there is a novel approach that was proposed. It uses the rationale behind the traditional weighted majority approach, but it can generate weights without using the ground truth data, which is our main objective in this umbrella. And for the second category, I have chosen to use the Dempster-Shafer fusion method. There is also a novel approach, Dempster-Shafer with context credibility, designed to accommodate the characteristics of the non-motorized traffic. So I will go into more details of each of the method in the following slides. So first comes the fusion method without the benchmark data. In the voting approach, first I will we explored the three different rationales or algorithms. First comes the unanimity voting, where a decision is made when all sources agree on the decision or a class level. And the simple majority, at least half of the sources has to agree. And in the plurality voting, a decision is made when based on the most voted classes. So weighted majority is another popular framework of fusion, where each classifier is given a certain weight of or importance in the final decision-making process. But in the conventional weighted voting, a weight is computed based on accuracy, which actually needs the benchmark data. So here I have proposed a weight estimation method that considers pairwise interaction of each of the data sources, meaning if one source has high dissimilarity with the other source, its decision in the final algorithms gets a low weightage, and vice versa. Yeah, next, thank you. So to evaluate the voting fusion, we have used the actual bike volume estimate from the 5 bike demand models IPAC mentioned for explaining the application and interpretation of the voting algorithms. The actual volume information from the 44 location was used. So in the picture, for the first picture, we can actually see the clear trade-off between the detection rate and detection accuracy, depending on what voting algorithm we have used. We can say unanimity has the highest accuracy, but the lowest detection rate, which is quite expected. So when we are preferring the accuracy over the coverage, maybe we should be considering unanimity or the simple majority voting over the other approaches. And I would like to note here that although in cases like ours, the increase in accuracy of the fusion over the individual estimate might not be that high, but it can still instill confidence in the estimate, which is also a very important objective of the whole fusion endeavor. So now comes the Dempster-Shafer fusion method, which is the core of our fusion framework. And I will go through the basic concept first. So given the characteristics of the non-motorized activity data, which is often scarce, vague, incomplete, conflicting, we needed a robust fusion algorithm to represent the knowledge and handle the uncertainty. And in this regard, actually, Dempster-Shafer was a suitable mathematical framework that elicits decision from multiple sources and measure the uncertainty involving the ambiguity and conflict. So the DST framework creates a frame of discernment using the classes, which is specified by the analyst, and then it creates a mass function or the basic probability assignment or BPA, which actually represents the degree of belief that supports a particular or multiple hypotheses. For this research, we used the most recently proposed approach that estimate per class, per source mass function using both precision and recall matrix. Finally, to accommodate the conflict of the sources, we used a distance measure which can reduce the strength of the BPA based on the conflict of each of the sources. And our key rationale behind this was the more one estimate for one location is in disagreement with the other, the more the estimate is unreliable. Hence, they are actually discounted in the final decision. So we also proposed an extension of the basic framework, DST, with the context credibility. So the concept of context error computing is actually not new. They have been used within the perspective of sensor fusion, where there is a need of sensing and managing contextual information. It has been defined as the information that can be used to characterize a situation or entity. So while the conflict-based discount I already mentioned computes the disagreement among the evidence, the proposed method estimates the discounting factor based on contextual situation, comparing with the ground truth data we have. Then the belief function of each source can be modified finally based on the contextual discount. So we found it really important especially for the non-motorized traffic data, where the reliability of the volume estimate for different sources may actually have a contextual variations like spatial or temporal. For example, a volume estimate for bicycle sharing data may be more reliable on spatial zones near the kiosk location than the farther. So for our case, we used spatial location as context. The framework can be applied in other areas as well, but identification of such context would require subjective judgment based on knowledge of the local condition, definitely. So in the proposed mechanism, the discounting measure based on contextual situation was estimated using the gray theory. Next, thank you. To evaluate the Damster-Schafer fusion, we relied on the artificially generated data set of different characteristics. So while generating the artificial data, I kept in mind a few things. First, the data should confirm the actual non-motorized model outputs for the study area, but should have a larger yet realistic range of non-motorized volume. To demonstrate the effective of the contextual discount, which we proposed in the study, the artificial data set should exhibit a contextual difference in terms of reliability in some form actually, which conforms to the actual scenario. So for this, I developed a set of randomly generated bikeability index values range from 0 to 60. Then I took reference from the direct demand model we developed to finally get a ground truth data based on the bikeability index. And then I actually generated the other data set, which were denoted as the individual sources. Also, each of the artificial data set was divided into two sets, context 1 and context 2, where the accuracy of the each sources varied. So for this, we developed 3 scenarios. Scenario 1 had no missing observation, fairly similar accuracy across the sources. Scenario 2 had also no missing observation, but the accuracy of the sources vary. Some source has really high accuracy and some very low. And in scenario 3, each of the sources has missing observations, and also the accuracy of the sources varied across each of the sources. So for each scenario, the data was characterized in 2 labels, first for 4 category and the second with the 12 categories. We wanted to analyze the sensitivity of the fusion mechanism across the category type. So I will go through the main takeaways of the DST fusion analysis using the simulated data of various varying scenarios. So first, I would like to note here that we cannot expect the fusion algorithm to always give a better result. It actually depends on data and situation. And fusion accuracy is definitely sensitive to categorization type. We investigated for the 4 and 12 categories. And more is definitely not always better. We cannot keep adding data sources and expect it to get better result. The accuracy gain also varies with the degree of conflict and the context credibility that we proposed, and it actually vary even for the same data set. It may vary with different categorization level. I would also like to mention here that when there is a lot of missing cases, even a comparatively lower accuracy sources may add value to the fusion process. So here we already had the fused estimate, and we utilized the fused exposure estimate to develop two separate crash models in the study area. First, we conducted an area or macro level hotspot analysis using crash measure, which took into account the weighted crash rate by injury severity and aggregated block level ADB as exposure measure. And we identified both cold and hot spots and found that hot spots were generally appeared in the central downtown region in the city. There are also some pockets of block group with cold spots in the relatively outer area in the northern region. And we also had a micro level crash analysis for the same study area to investigate the, here we actually investigated people's perception regarding safety related impedance of biking. And for that, this research took advantage of the 2017 NHTS survey. We wanted to investigate which issues tend to influence people's frequency of not biking more. So we had two logistic regression model, which utilized a rich set of explanatory variables and found that people's perception were associated with the built environment features of the neighborhood around the individual's home location, and in addition to their demographic characteristics as well. And most importantly, we found that the bicycle exposure we estimate from the fusion, it was found to be an important variable in the model. So I'm here, the final remarks will be delivered by Vivek.
Thank you very much, Sylvie. I would like to conclude our presentation with some final remarks about our findings and the overall project. First of all, this study contributes to both research and practice by providing a structured and systematic evaluation of fusion process for non-motorized traffic. We were looking for a generalizable approach, which had a lot of constraints, as Sylvie mentioned, but we had to take into account examining the unique characteristics of non-motorized data, exploring various different fusion mechanisms, and selecting the one that will be reflective of the data to the extent possible. We did have an opportunity, though, to work with both traditional and crowdsourced data, which provided great insights into their potential or limitations to use in a fusion framework. And various models that we developed as part of this project help us better understand the bicycle activity in Austin, as well as the potential safety issues and safety concerns, perceptions in the city of Austin, and can be utilized independently or as part of a fusion algorithm as needed or desired. And as I briefly mentioned earlier, it's scalable. So any of the models, the framework, and the algorithms developed in this study can be adapted at other areas. It needs to be localized, it needs to be revised based on the characteristics of the other areas, but it will be adaptable. And I would like to emphasize that the beauty of the decision fusion mechanisms developed in our study is coming from their flexibilities to support the utilization of the local knowledge and the data to either use the individual estimates or opt for the fusion approach in an effort to obtain a better estimate or more reliable estimate with increased confidence. So that was very important for us. And as Sylvie mentioned, we cannot really expect that the fusion will always give the better results. So, and we didn't start with this mindset at the very beginning of our project. But as we move forward in the project, we realize more and more about the importance of being flexible in developing or applying the fusion algorithm, especially in the context of transportation and non-motorized travel and safety analysis in particular. So perhaps it is important to design the frameworks to facilitate the decision-making process, to implement most effective strategies in a feasible way instead of making it as the end goal. So the local knowledge, evaluation of the resources available, how they can feed the process, how they can feed each other, what they bring to the table, how confident we are with them, and so on, all play very important roles in deciding how we move forward with the fusion. And the fusion can include one single source or multiple sources. So this is a decision to be made by the local expertise, by the technical expertise, and by the information that we have related to our data or the case study. So this is really the end of our presentation. I would like to conclude by acknowledging our team member, Dr. Yunlong Zhang, in addition to presenters Sylvia and myself. And last but not least, we are really very thankful to have support from various agencies and individuals, either in accessing the data, compiling, understanding, processing the data, or just for their great feedback, guidance, and review at different stages of the project. So this project would really not be possible without their support. So thank you very much to all of them again.